Hi, everybody. So today we are going to spend some time talking about standing waves on strings. Now, I want to start off by saying that we are going to both build on and then focus within on some of the things from the Khan Academy video I asked you to take a look at last week. If you haven't watched that Khan Academy video yet, pause this, put it away for a second, go back and watch the Khan Academy video on standing waves and strings that I posted last week. I want you to see that first. Then I want you to come back and I want you to see how I want you to focus, the pieces that I want you to focus on, and the way I'm going to expect you to learn to talk about this. A lot of it's the same, but I just want to make sure that you are meeting the learning targets that we have for this class. Okay. So, with standing waves on strings, the most important thing to remember from what we've talked about before last week with reflection and superposition and interference and all that, standing waves are a very specific example of interference and reflections of waves. When you send a series of pulses, a series of waves down a string, and they hit a fixed end, they reflect back in a certain way. And only if you send those waves at a very precise frequency will the waves create a standing wave. Will those reflected waves create a standing wave? And you saw a lot of examples of that last week on the videos and the simulations that I asked you to do and work with and play around with. And again, if you didn't do those things or if you didn't see those things when you did those things, go back and mess with that some more. Okay, either now or after you watch today's video. All right, so these standing waves only occur at very precise frequencies. And the cool thing is they occur in very precise patterns of frequencies. So today, what we're going to focus on, or begin to focus on, because we won't get through it all today, are the mathematical and musical, for those of you who are music students, the mathematical and musical relationships between the patterns of the formations of the standing waves on string. If you play a stringed instrument of any kind, or really any instrument of any kind, this is going to be right up your alley. So let's take a look at the first standing wave that is formed on a string and what it looks like. First of all, let's talk about the situation we're working with, right? What's the material? What's the equipment we're dealing with? So when we're talking about a standing wave on a string, we're talking about a string, and this horizontal line represents my string that is fixed at both ends. The string, got to get another color marker. The string is fixed at both ends, and we're going to say that this string is L long. Now, that L could be anything, right? If it's a ukulele, it's a relatively short L. If it's a violin, it's a relatively short L. If it's a guitar or a viola, it's longer. A cello, a bass, still longer. But this L represents how long this string is. And we want to leave it with L because we want it to apply to any situation. We want it to be generic or general in nature. So we're just going to talk about strings that are L long. That could be a meter, a half a meter, 3 meters, whatever. All right, so we have a string here that is L long. And when we pluck this string or bow this string or strum this string or any number of things you can do to a string to get it vibrating to create a sound, to create a musical note, when we pluck or play this string, it's going to tend to vibrate in what we call the fundamental frequency. Now, that's the musical term that we've adopted in physics, but that's the musical term for the precise frequency standing wave that is formed when you pluck or bow or play a string that is fixed at both ends. Okay? That is the lowest frequency standing wave. That is the lowest frequency standing wave you can get for any vibrating string. You can't get a string to vibrate with a standing wave at a lower frequency. You can't wiggle it at a lower frequency and produce those nice pattern of waves that make it look like it's standing still. You can get all kinds of weird wave patterns going on in there. And if you played with the simulation last week, you saw that happening, right? But the lowest frequency standing wave, where it looks like it's standing still, happens at what we call the fundamental frequency, or in physics, we often call it the first harmonic standing wave. All right, so what does that look like? What does that first harmonic standing wave look like? Well, again, if you watched the videos and the simulations last week, you saw that it looks something like this. It vibrates in a way that it makes kind of a arc, right? Where there is maximum displacement from equilibrium in the middle. We call that an antinode. And at either end, where it's fixed, we have these things called nodes. So we have a node at each end and an antinode in the middle. That's the first harmonic standing wave. The fundamental frequency of vibration for this string happens. Now, as you might imagine, it doesn't just vibrate up, right? When you pluck a string, it goes up and down. But it goes up and down in a way that makes it look like it's standing still. That's why it's called a standing wave. If it's a standing wave, this middle is going to go up and down, but it's not going to move back and forth. At least it's not going to appear to look back and forth because of the interference pattern, because of the way the waves are reflecting off either end and interfering with each other. It looks like it's standing still. And again, go back to that Khan Academy video if you haven't. So the antinode vibrates the most in the middle. Nodes vibrate not at all at the ends. That is what we call the first harmonic standing wave of a string. Now, one more quick thing we're going to talk about here. What is the wavelength of the string, right? It's the fundamental frequency. It's the lowest possible frequency, but we know that waves have speeds, frequencies, and wavelengths. Those are all properties, measurable quantities of waves. So the frequency is the lowest frequency, and that's going to depend, if you know anything about music, that's going to depend on the kind of string you have, how thick the string is, how long the string is. We don't really care right now. All we care is that it's the lowest frequency. You can't get a lower frequency than this kind of vibration, this first harmonic vibration with an antinode in the middle and nodes at either end. So the question is, what's the wavelength? Well, as they showed in the Khan Academy video, this represents 1/2 of a wave, because a full wave goes up and then down and back to where it started. That's a full wave. This is half. This is either that half or this half. So if you have half a wave vibrating on a string that is L long, clearly if this is L, then the other half would also be L, and the wavelength is 2 times the length of the string. So if your string is 1 meter long, your wavelength of the first harmonic is 2 meters. If your string is 20 centimeters long, the wavelength of the first harmonic on that string would be 40 centimeters. So you can see with different length strings, you can get different frequencies of vibration, different fundamental frequencies, because the length changes the wavelength, and that changes the frequency. All right, that's enough for right now. Feel free to go back and review these anytime. We'll do more later in the week. We'll talk more about what about other frequency standing waves? What about the second harmonic? What about the third harmonic, right? What happens there? How do they look different? And mathematically and musically, what makes them different as well, okay? But this is a good start. Maybe take a look at this again. And again, if you haven't watched those Khan Academy videos and the simulations from last week, go back and mess with them some more and do the reading in the chapter as well. Thanks, everybody.